Okay, so we're pleased to have as our speaker today Dylan Airey from the University of Texas, Austin. And he's going to speak about the Borel complexity of generic points assuming the specification property.
Okay, thank you. So to start off, I want to motivate this talk by just recalling probably one of the most fundamental theorems of dynamical systems, and that's Birkhoff's pointwise ergodic theorem. Right, so what does this say? It says that if you have x equal to a Polish space, that is, it's a separable, completely metrizable space. And if you have a map T from x to x, which is measurable, where we put the Borel sigma algebra on X, that is the Borel sigma algebra generated by open sets. And you have a measure mu, which is T invariant on X. Then the following holds. So then for mu, almost every x in X, we have that if f is a continuous bounded function on X, then the following limit is, or we have the following formula for the this limit. So you take the limit as n goes to infinity of 1 over n, then the sum from 0 to big N minus 1 of f of t to the nx. So in other words, you're averaging your continuous bounded function over the orbit of x. That this is going to be equal to the conditional expectation of your continuous bounded function on the sigma algebra of invariant sets, of t invariant sets, evaluated at x. Okay, so in particular, when mu is ergodic, this sigma algebra is trivial, and so so when mu is ergodic, this is just equal to the integral of f d mu. Right, so what's this theorem really saying? Well, it's saying that if you pick a typical point in x according to your measure, and you look at the time average, that is the average over the orbit of x, you get the space average, right? So, very classical, very nice theorem. And it motivates the following definition of what's called a generic point, right? So what this theorem is really saying that is that sort of the generic x is going to satisfy this time average is equal to space average property. So, generic point for a dynamical system x t mu is a point x in x such that for all continuous bounded functions on x, we have that the limit as n goes to infinity, 1 over n, so minus 1.
Sorry.
Right, so right, yeah, this is the definition of a generic point for a dynamical system. Right, so in particular, by this theorem, we have that if mu is ergodic, then almost every point is generic. Okay. So what's an alternative way of saying this? Well, consider the following sequence of measures defined by 1 over n, sum from n equals 0 to n minus 1, of the point mass at t to the nx. What this theorem is really saying then is that this weak star converges to mu. This is an alternative character.
Yeah, sorry to interrupt you, but I'm a little rusty on the ergodic theorem. So are you saying that there is a set of measure 1 that's independent of f? Or, or is
sorry.
it for every f,
for every
there
f,
is a set of
it's
measure?
for every f, it's a set of measure 1.
So a generic point is something really strong then, because you want a point x that does for every.
So because x is Polish, so for example, think of like the unit interval here, then the bounded continuous functions actually have a countable dense subset. And so in particular, if this is satisfied for that countable set, then it's satisfied for every continuous function. So it's actually not too strong. You're just taking countable intersection and measure 1 sets. Thank you. Okay. So this is an alternative characterization of being a generic point. Just saying that you know, the uniform measure on the first n orbit segment of x is weak star converging to mu. Okay, so you know, let's look at a particular example of a dynamical system where we can actually, you know, like see what a generic point should look like. So the example I'm going to introduce first, we let x be the unit interval 0 to 1, closed at 0, open at 1. We let t of x be given by bx mod 1, where b is a natural number and b is also greater than or equal to 2. We just let mu be the standard Lebesgue measure. Right, so this is, you know, a very, very nice dynamical system. It's Bernoulli, it's ergodic, it's all these sort of nice properties. And so for this particular example, what does a generic point look like? Well, the way to see this is by looking at a symbolic representation of this dynamical system. So in particular, if we write x, we can always expand x in its base b expansion, from n equals 1 to infinity, as a sum of x sub n b to the n, where x sub n is in 0 through b minus 1. And also x sub n is not equal to b minus 1 infinitely often. Then this expansion is unique. Okay, and so what's the point? Well, if you take this map phi from 0, 1 into b to the n, which is given by mapping x to its base b expansion, well then this is actually going to be you know, a nice isomorphism from this dynamical system to just the shift on b to the n. And now the push forward measure of Lebesgue under this map is going to be the uniform measure of b to the n. Okay, and that's really nice because you know, b to the n here is a very like nice zero-dimensional space, and so in particular we can find you know, a good countable subset of the continuous functions, such that if this limit it holds on that countable subset, then it holds for every continuous function. And that's given by the indicators of cylinders. So in particular, what this means is that x is normal, or is generic for this dynamical system, and in particular for this dynamical system, we call generic points normal in base B. If for every block B, which is a finite block consisting of letters in 0 through b minus 1, we have that the limit as n goes to infinity of 1 over n times the number of times in between 1 and big N, such that we see the block B in the B area expansion of x. So that is that xn is equal to b1 all the way up to xn plus k minus 1 is equal to bk. If this limit is equal to b to the minus k. Right. So this is sort of the original definition for being a normal number in base B, well, not the original one, but Borel introduced normal numbers in base B back in 1909 and showed that almost every, with respect to Lebesgue measure, almost every number is normal in base B. He didn't use the ergodic theorem here, but it follows immediately by.
So basically, if x is normal in base 2, that means the number of appearing 0 and 1 is the same.
Yeah, it's even stronger than that because every block of 0, 0 occurs at the same frequency as like 1, 1, for example.
Okay.
Right, so this is what a generic point for this dynamical system looks like. Okay, now you might ask questions, what properties does the set of normal numbers have? So it's full.
Well, when you say normal numbers, you mean normal in every base? Or
Normal in base B, sorry.
For specific?
Yeah, for specific. We're only looking at one dynamical system at a time.
Okay.
Yeah. So it's going to be full Lebesgue measure, just by the ergodic theorem, because this dynamical system is ergodic. It's not too hard to show that it's actually also a meager set. That is, it's a countable union of nowhere dense sets. Right. And you might ask, for other properties of normal numbers. And you might ask for other properties of generic points for other dynamical systems. There are other interesting dynamical systems people care about, like the continued fraction dynamical system, which is associated to, the continued fraction expansion of a real number. Or if you allow, for example, b to not be an integer anymore, then you get what are called beta expansions, which are discontinuous dynamical systems on the unit interval. And you might ask, okay, what's a generic point for these guys? And so in order to answer that, one thing I want to say first is about normal numbers, right? Is let's look at this characterization of normal numbers again. What's this really saying? Well, it's saying that for every b in b to the k, or well, first for every integer k, and then for every block b, for all epsilon greater than 0, there exists an n sufficiently large such that for all n greater than big N, we have that 1 over n times the number of recurrences between 1 and n, such that, and also, instead of writing this out, I'm just going to use the notation n to n plus k minus 1, that this is equal to bk. Now, minus b to the minus k, that this is less than epsilon. Okay, so this is an alternative way of characterizing the set of normal numbers in base b, right? It's all the set of all x such that this long string of quantifiers and then this property hold. Okay, but what is this really saying? So if you look at just this statement first, what are the set of x that satisfy this property? Well, whether this property is true or not only depends on the first finitely many digits, of x, right? So in particular, in the natural topology we put on b to the n, what you get is that this is really the set of x that satisfy this is both a closed and an open set. It's quota. Okay, then what do we do? Well, we take a for all n. So in other words, we take a countable intersection. Then we have an exist, so it's a countable union. And then another countable intersection, we can take epsilon rational, so it actually is countable. And so what we get is that the set of normal numbers is a countable intersection of a countable union of a countable intersection of Clopin sets. So now the question is, can we do better? Can we write it, for example, as a countable union of a countable intersection of Clopin sets? Or is even the set of normal numbers closed? So in order to answer that question, we need to introduce some machinery, and this is the Borel hierarchy. Okay, so again, we're going to let x be equal to some Polish space. And again, we're going to consider the Borel sigma algebra on x. Now, the Borel sigma algebra is generated by open and closed sets. So in particular, any measurable set can be written as a sequence of countable unions and countable intersections of closed and open sets. So what we can do is we can write a way of exhaustively listing all measurable sets. So first, we define the class sigma 0, 1 to the open sets in x, and the class pi 0, 1 to be the closed sets. Then what we do is we take countable intersections of open sets to get the next class, pi 0, 2. These are also called the G delta sets. Yeah. And then we can take countable unions of closed sets to get the class sigma 0, 2. This is equal to the F sigma sets. And then we can continue, right, by taking countable intersections of sigma 0, 2 sets, which you get pi 0, 3, and countable unions of pi 0, 2, we call these sigma 0, 3. And we also define a third class, which is just the intersection of the sigmas and the pi's. So delta 0, 1 are the clopen sets, delta 0, 2 are the sets which are both F sigma and G delta, delta 0, 3, both pi 0, 3 and sigma 0, 3. And we have the following containment relation between every one of these classes. So open sets are delta 0, 2 as our pi 0, 1 sets, and sigma 0, 2 sets are delta 0, 3. And you continue this on. So in particular, what's the actual definition of a sigma 0 alpha for a countable ordinal alpha? So let's let alpha be a countable ordinal. Then we say that A is in sigma 0 alpha if there exists countably animated ordinals alpha n, which are less than alpha, and an in pi 0 alpha n, such that A is equal to the union of the ANs. Right, so we take countable unions of pi 0 alpha sets to get, or pi 0 alpha n sets to get sigma 0 alpha sets. And then for pi 0 alpha, you just do the same thing but switch pi and sigma. Right, so this is the definition of a sigma 0 alpha set. Okay, so what does this computation here show us? Well, it shows us that the set of normal numbers in base B is a pi 0, 3 set. And so the question we want to know, or the question we want the answer to now, is the set of normal numbers in base B in any lower complexity class?
Suppose it is. So what? What does it give you? I mean, I don't understand. Does it give you any? I mean, I'm not trying to be smart here. I'm just. I mean, so does it give you any insight to some?
It tells you sort of how complex like your generic points are, right? And your generic points are sort of like they have all the information of your dynamical system. If you take any generic point and you look at its orbit closure, and then you take this measure, you get your original dynamical system back.
So do we know that, I mean, can you immediately see that they're not closed or open? I mean, is it...
Certainly because there do exist non-generic points. And so if you had a closed measure 1 set on the unit interval, that would have to be everything. Yeah. And so, I mean, for example, like 0 isn't a B-normal point for any rational number is not normal in base B, so it's certainly not closed. But maybe it's a G delta set, or maybe it's an F sigma set, but it's kind of hard to see a priori.
Nice. Okay.
So the notion we need for not being in a lower complexity class is that of pi 0 alpha and sigma 0 alpha hardness. So we say that A is sigma 0 alpha hard if it's not in any lower complexity class. In other words, if A is not pi 0.
So, I'm sorry, because, so normal numbers in my tiny world, I can find this are normal to every base.
Oh.
So this will be, no, who cares, but this will be higher in the hierarchy, or it has nothing to do with this hierarchy?
Well, because that'll be a countable intersection of pi 0, 3 sets. So
for sure, so it's, at face value it looks to be higher, but is it really higher? You're adding you're adding a qualifier.
No, sorry. Absolutely normal numbers are pi 0, 3 complete. That is a theorem.
Absolutely? What is absolutely?
Pi 0, 3 is closed under countable intersections.
I see. Okay, fair enough. Okay, fair enough. So even though that they seem to be higher, but they're actually in the same, okay, fair enough.
And in fact, they're not any lower, actually. There's a theorem that says that,
Really?
but that's,
Why are
but I'll get to that.
Saying there is a base where it's normal is what raises the complexity.
Yeah, so for example, if you ask for the set of numbers that are normal in some base B, that's a sigma 04 set, because that's a countable union of pi 03 sets. And it's actually not any lower than sigma 04 either.
I see, okay.
Theorem of Becher and Slayman.
Okay, thank you, yes.
Say again, see?
The theorem of Becher and Slayman.
I see, okay.
So if A is sigma 0 alpha hard, if it's not in pi 0 alpha. So in other words, what this means, right, is that say you have something that's in sigma 03 and you don't want it to be in any of these lower complexity classes. Well, if it was in pi 0 alpha, it would be in this lower delta 0 alpha class. And so that's why we take this sort of simple looking definition for hardness. Okay. And furthermore, we say that A is sigma 0 alpha complete if A is sigma 0 alpha and sigma 0 alpha hard. So we know that the normal numbers in base B are pi 0, 3. Now what we want to know is that they're pi 0, 3 complete. And this is true. This is due to Ki and Linton. And what this says is that the set of normal numbers in base B is pi 0, 3 complete. So in other words, we can't write the set of normal numbers in any simpler way. Okay, now how do you actually prove pi 0, 3 completeness results? You use a method called the reduction method. This is actually a pretty commonly occurring type of argument. So what the idea is to take some set that you know is pi 0, 3 complete and reduce the question of containment in this set to just the containment in the set of normal numbers in base B. If the set of normal numbers in base B were any simpler than pi 0, 3, then this set that we know is pi 0, 3 complete could not be. So in math, what this is we let x and y be polar spaces, and we have measure sets A in x and B in y with a continuous function f from x to y, continuous, such that f inverse of B is equal to A. So this continuous map is our reduction map. And then the result is that if A is sigma 0 alpha complete, or actually just sigma 0 alpha hard even, then B is sigma 0 alpha hard. So what's the argument for this? Well, suppose that B wasn't sigma 0 alpha hard, and so could actually be represented in some lower complexity class. Well, taking the inverse of a countable unit or of a union and intersection just allows you to take the intersection and union outside of the inverse. And then we're left with some countable unions and countable intersections, and then f inverse of closed sets.
Sure.
But f is continuous, and so in particular, we're going to get that A is a countable union and countable intersection of closed sets. And if B was any simpler than sigma 0 alpha, then in fact A would be as well, but since A isn't, B can't either. Right? And this type of argument is pretty common. For example, in like computability theory, you reduce the halting problem to problems you want to show are not computable. The same idea. Okay. So armed with this method, this theorem is actually not so hard to prove. So here's how it works. So first, we need some polar space and some pi03 complete set inside this polar space. So the one we are going to work with, we're going to look at n to the n with topology given by pointwise convergence. It's a very nice polar space. And we're going to let C3 be equal to the set of all sequences in n to the n, which tend to infinity. Then this is a pi03 complete set. Okay, so what do we want? What we want is a continuous function from n to the n to the unit interval, such that if beta is in this C, then we get a normal number, and if beta is not in C, we don't get a normal number.
What's the definition? C?
Sorry, this is the set of all sequences of natural numbers that tend to infinity.
And this is
This is pi03 complete. This is known.
Forever exists forever.
You want to.
Oh, yeah, okay. When you put the point, yeah, sure, okay. I see, okay, fine.
Okay, so how do we do this? Well, the way we're going to do this is by saying, okay, let first we fix u a normal number base b. So we're going to start with some normal number. Then what we're going to do is, let's write out u and its base b expansion. So this is n here. What we're going to do is we're going to split up the natural numbers into very large windows. And then what we're going to do is we're going to alter the expansion of u on these windows according to our function, our sequence beta here, such that if beta is in C, then in the limit we're not changing any of the digit frequencies of u. And if beta is not in C, then we are going to mess up some frequencies. And so we'll get that, this is actually, we're going to get a valid reduction map on this. Okay, so in particular, what we're going to do is we're going to define a very quickly increasing sequence, an, such that what happens in A1 to A2 is going to be much, much, much greater than what happens between 0 and A1. And then for all these higher ones, we just have something very quickly increasing. Okay. All right, so what do we do? Well, let's define our function f of beta. So we're going to define this by specifying the kth digit of f of beta. So this is going to be equal to u sub k if an, okay, so what we do is we look at our nth window, and we copy down exactly the same digits of u as before, but now at this little last 1 over beta of n portion, we're just going to put all zeros. Okay, so first, this map is actually continuous. The way to see this is that the kth digit of f of beta is only going to depend on finitely many values of beta. And so because we're working with the topology by pointwise convergence, this is continuous. So
Did I miss the definition of the ANs?
Yeah.
Sorry, A is just some quickly increasing sequence. So just very, very quickly increasing.
Does it matter how quickly, like exponential or?
It doesn't really matter. You just need it quickly growing enough so that the frequencies of the digits you care about in U show up with what they should, or how often they should.
So this last little segment doesn't actually change much, or?
Yeah. Well, I mean, it's going to change something by a non-trivial amount if beta of n is equal to a constant infinitely often, but we'll get to that. So n is just some quickly increasing sequence. You can write down the sort of exact details that you need, but it's not super important. So f is continuous. Now let's suppose that beta is in C3. Well, then f of beta is actually going to agree with u, except on a set of density 0. Right? And why is this? Well, because beta of n is tending to infinity, in each one of these intervals, a decreasing fraction of the digits are changed to 0, right? Where this fraction is going to 0. And so in the limit, we're changing a set of density 0 of digits. And so in particular, because we only care about sort of limiting behavior, this doesn't affect normality. So this implies that f of beta is B normal. Okay, now what if beta is not in C3? Well, if beta is not in C3, that means it's not tending to infinity. So we can find some finite value where beta of n takes on that value infinitely often. So in particular, for infinitely many of these intervals, we're going to have 1 over beta of n of the digits being equal to 0. Now, because we chose these ANs to be quickly increasing, so that what happens in this interval here dominates what happens in all the previous intervals, we're actually going to get that the digit 0 shows up more often than it should. Right, and so in particular, f of beta is not B normal.
Right.
Okay, and so these are the conditions for a reduction map, and so we get that the B normal numbers are pi 0, 3 complete. So we get an upper bound of the complexity of the normal numbers by this, and we get a lower bound of the complexity of the normal numbers by the reduction method.
Wait. So to be pi 0, 3 complete, you have to be pi 0, 3, but not sigma 0, 3, right?
Yeah. So we didn't.
So is there an equivalent of the statement with pi, like, is there something like pi 0, 0 alpha hard, or?
Sorry, yeah. So these definitions also go through for pi 0 alpha and pi 0.
You can
just
just pi instead of sigma.
Yeah, you just like replace sigma with pi and pi with sigma. So
Right.
yeah, sorry. Okay, so this is the proof. And I want to make a couple of remarks about the proof. What is really the structure going on in this dynamical system that allows this to work? So one, we can start with some generic point that we can then alter such that we get the desired frequencies. And two, we have enough freedom to change things in a way that we can actually affect frequencies. So these are sort of the two key properties going on in this proof. And so you might ask, okay, what dynamical systems do we also get pi 0, 3 completeness for the generic points? What dynamical systems does this argument kind of work in?
It's just, since you're going to go into things which I'll understand even less. But, so, if you look at the numbers which are normal to no base, which we know have a house, from Schmidt's game, it has a big dimension, so it's in, this would be where the hierarchy is. So Logan is telling me it's going to be sigma 0, 4. Numbers which are normal to no base. Can you use the same reduction techniques to show that they are hard?
Let's see, so...
That would be a pi 0, 4 set, right? That would be a complement of vector sign.
Yeah, okay. Right. Yeah, so, So so it should be pi 0, 4, because the point is that the set of numbers that are normal in some base is sigma 0, 4 complete, and so you take the complement of it, it's going to be pi 0, 4 complete.
And it's hard because it's coming from some easy consideration here?
No, actually, the proof for the Becher-Enslavement result about sigma 0, 4 completeness of the set of normal numbers, or set of numbers that are normal in some base, actually uses some pretty complicated arguments with like exponential sums and all sorts of weird techniques that I don't really understand. But yeah, so it is kind of a tricky argument.
So it cannot be reduced.
Right, yeah. You can't reduce it below pi 0, 4 for the set of numbers that are normal in no base.
Okay. All right.
So that is pi 0, 4 complete. Okay. Sorry, going back to this. What dynamical systems would an argument of this sort of form work for? So we can immediately rule out a couple. So example 1, we let x be 0, 1, open at 1 again. T of x, the irrational circle rotation. So alpha. And again, mu equal to big. Okay, well, the sequence n alpha is always uniformly distributed modulo 1. And so in particular, shifting it by addition by x isn't going to change that. So actually every point is a generic point. Also, I'm going to start using the notation g of mu for the set of generic points, so I don't have to keep writing that. So in fact, g of mu is equal to everything. So in particular, this is a delta 0, 1 set. Okay. Example 2. Right. We let x equal 0, 1, t equal to the identity map, and mu equal to the average of the point masses at 0 and at 1, then in fact the generic points are going to be empty. Which is again a delta 0, 1 set. Okay. Example 3. So we again let x equal 0, 1. T of x is given by 1 minus x, and our measure is the point mass supported at 1/2. Then g of mu is equal to the singleton 1/2, which is a pi 0, 1 complete set. Okay, so we get pi 0, 1 here. The last example I want to give, or well, for now, this is due to Falmiauska, or Falmiauski. Kusinski. Kwietniak, or a co-author on this paper.
No easy names then.
Yeah, well, the last one is.
And John.
And Lee.
Oh, Lee.
Yeah. So what they do is they construct x equal to a closed subshift of 2 to the z with the following property. So such that every point is periodic, or it has the property that the frequency of the digit 0 is 1. So this makes sense, either every point's periodic, or almost every digit you have in the sense of density, asymptotic density, is equal to 0. Right, so they construct this closed subshift, and so in particular, what you can take is mu equal to the point mass at the sequence of all zeros, and then the generic points are going to be equal to exactly the set of x with this property. Okay. Another property of this dynamical system, or of the subshift, is that actually the periodic points are dense. So the generic points are exactly the complement of the periodic points, so they're the complement of a dense countable set. And the complement of a dense countable set is pi 0 2 hard. So,
Right.
in fact, pi 0 2 complete in this example. Okay. So, one more thing I want to mention is, for the dynamical systems, we only assume that our shift map is measurable. But for this, in order to get any sort of result about generic points, we're going to need to assume continuity. Reason being that any Borel subset of 2 to the z is Borel isomorphic to 2 to the z. And so in particular, the set of normal numbers in base B is Borel isomorphic to 2 to the z. So what this means is that, let x equal 2 to the z and y equal your generic points. So then we get some Borel isomorphism from y to x. And then what we do is we consider just the big measure on y again. So equal the big, restricted y, which we can do because it's a measure 1 set. And then let's define the dynamical system given by x. Phi inverse composed with the shift, composed with phi, and then the push forward under this map of the Lebesgue measure. Then what's going to happen is that actually every point in this dynamical system is generic. Right, but what's the problem? Well, the problem is that this isn't necessarily continuous, and so certainly this isn't going to be a continuous dynamical system. So we do want to assume continuity, which all of these examples, they do have their shift being continuous. Okay, so looking at these examples again, what are some properties that they all have in common? Well, sort of the first thought that we considered was they all have 0 entropy. Right?
They all have, sorry, continue.
They all have a 0 measured theoretic entropy.
Okay.
And entropy says that it's the exponential growth rate of the number of finite strings that are approximately equidistributed with respect to your measure. And so the idea is maybe, okay, well, if you have positive entropy, maybe there's enough room in here that you can alter your generic point and get something in such a way that this proof goes through. Unfortunately, that doesn't turn out to be true. This can be seen with the following example. And this is due to Hahn and Katz-Nielsen. So what they do is they construct X, closed subshift, with positive topological entropy. And which is uniquely ergodic. That is, it has a single invariant measure, which is necessarily ergodic since the ergodic measures are the extremal points of the set of all invariant measures. Okay, so what's this example show us? Well, take your unique ergodic measure for this closed subshift, and look at any point x in here, and consider this measure given by this guy. Okay, so this is a probability measure. The space of probability measures is compact if x is, which this is going to be on a finite alphabet, so it is compact. And so in particular, we can find some convergent subsequence of this guy. Furthermore, because of the way that these are constructed, this is also going to be an invariant measure. And so necessarily, since there's only one, this is going to have to converge to the single ergodic measure that we have. And so in particular, we have that every point is generic. So G of mu is again equal to everything. So this is positive topological entropy. Since topological entropy is the supremum of measure theoretic entropies. In fact, and there's only one invariant measure, we have that both positive topological entropy and positive measure theoretic entropy aren't enough to get pi0 completeness of your generic points. So we need something else. And the something else, it turns out to be what's called the specification property. And this is a property that's been pretty widely studied, especially recently. It was first introduced by Rufus Bowen in his axiom-A diffeomorphisms paper. And sort of roughly the idea of specification is that it allows you to stick together any finite subwords that are allowed into another allowed subword in certain aspects. So that's the property that we use. We use specification. And just to note, this B shift on the unit interval does have specification, and a whole wide class of dynamical systems do as well. Every subshift of finite type has the specification property. Continued fraction expansions satisfy it. Beta expansions, even though they're discontinuous, turn out to satisfy specification. That's enough to make our proof work for those as well. So it's a pretty common property, which is very nice to have. Right. So there's also 14 different variants of the specification property. Unfortunately, there's periodic specification, there's weak specification, there's almost weak specification. There's I don't know why they're named. They have a very weird set of names. So we prove two main theorems where we use different notions of specification for the specific examples we care about. So the first theorem is in the symbolic case. So what this is we let k be finite or countable, or countable alphabet. We're going to show that for symbolic systems over K with some form of specification that we get pi0 through completeness for the set of generic points. So part A, if X is a closed subshift of K to the Z, or K to the N, doesn't really matter, with the right almost star specification property, which I will define after I actually state the theorems. Okay, so you have a closed subshift with the right almost star specification property, and more than one invariant measure then for any invariant measure we have that the set of generic points is pi0 complete. And part B of this theorem, I guess I'll put it up here, is that if x in A to the z is a shift invariant G delta subset, with the periodic specification property, which is actually the original specification property defined by Roots-Bowen. And again, at least two invariant measures. Then for any mu in which is shift invariant, we have that G of mu is pi 0, 3 complete. Okay. So what is the actual definition of the specification property that we use? It's as follows. So definition for a subshift x, or we say that x in k to the z has the right almost star weak specification property. If the following property. So we define the language of x to be the set of all allowed finite words. So if, just make sure I'm stating this right. So if there is a set G in the language of x, so some subset of the allowed words in x, such that for any u in G, or sorry, such that for any epsilon greater than 0, there is an n equal to n of epsilon such that if u and v are two words, two finite words, which have a length at least n, and u is in G, then there exists a v prime, also a finite word, such that the length of v prime is equal to the length of v. The Hamming distance from v to v prime is less than epsilon. So in other words, the fraction of indices where v and v prime disagree is less than epsilon. such that u v prime is also in our set G of a subset of our allowed words. So in other words, what this is saying is that if you take any element in G and you want to append to it some finite subword, as long as that finite subword is long enough, you can find something else which is, does it have to be in G? No, it doesn't. Okay, yeah. You can find some other word that is epsilon close to the thing you want to append, such that when you actually add it on, you get an allowed word, which is again in G. Okay. So this is the definition of right, almost star, weak specification property. And so any subshift which is closed and satisfies this more than one invariant measure is going to have pi 0 through completeness of the set of generic points for.
You said weak specification, but not in the theorem?
Wait, sorry?
You have the word weak there.
Sorry, this is right almost star weak specification.
Right, and then, but in the theorem you're assuming...
This is also right almost star weak specification. Okay. Yeah, yeah. So if our subshift has this property, has that property.
Okay.
Okay. Okay. So how does the argument go? It's sort of morally similar to the argument
for
Ki and Linton.
no, it's pretty clear where you need this thing, and it's pretty clear where you need more than one invariant measure, because otherwise you get to this Katz-Nelson.
Exactly.
Pattern.
Yeah. So the assumption on more than one invariant measure is just sort of a
To avoid
to
the
get rid of these
exactly.
incidents. All right. So how does the proof go? So we're actually going to use the exact same pi 0 3 complete set. So again, we're going to consider the polar space n to the n, and we're going to let C3 be equal to the set of all beta in n to the n such that beta tends to infinity. Right, so this is our pi 0 3 complete set again. And then we want to define our reduction map. So how do we do this? Well, again, we're going to start with the generic point. Well, actually, first, so say that we want to show that for mu in here, we want to show that the generic points is pi 0 3 complete. Well, since there's at least two invariant measures, we can pick nu, which is different to mu. And then what we're going to do is we're going to take two generic points, but one is generic for mu, and z is generic for nu. Now, we don't assume ergodicity, again, in this theorem here, so the existence of generic points is automatic, but it turns out that the right almost star weak specification property does imply the existence of generic points. Okay, so we're going to take these two guys, and now we're going to define sequences an and bn, depending only on x and z. Both of these are going to be sort of very quickly increasing. And also cn, an auxiliary sequence which is going to depend on beta. With the following properties. So these are that, an plus 1 is greater than or equal to 2 to the n times the sum, well, the previous an's. 2, an is greater than 2n to the n, 1 over 2 to the 2n. 3. So if you have any subword of x, you can look at its empirical distribution defined by just counting the number of times blocks of finite length show up. And so what we want is that AN is sufficiently large such that if you look at x from 0 to AN, this is epsilon close to mu. Now, to actually say this, you need to fix some nice metric for the weak start topology. And in this paper, we used the Prohorov metric, but the exact metric is important. So it's purely a topological result in this case. So 4. And what we want is that z 0 AN is also epsilon close to mu.
Is epsilon like 1 over 2?
Sorry, yeah, epsilon is like 1 over 2 to the n. Yeah. Okay, so these are properties we're going to have on the sequences AN and BN. And then what we're going to do is look at the following finite words. So what we do is we let U1 equal x from 0 to A1. And then we repeat it B1 times. We let U2 equal Z from 0 to C1. We let U3 equal X from 0 to A2. Repeated B2 times. U4 equal to Z from 0 to C2, and so on. So the idea is that, just as before, we're going to try and paste together these finite words to make an actual, expansion. And the point is that if C1 is sufficiently small compared to A1 times B1, or sorry, if Cn is sufficiently small compared to An times Bn, then most of the time, the point you're defining is going to have the same orbit as just x. So it's going to be mu uniformly distributed, and so mu generic. But if C1 or Cn is some infinitely often some non-negligible fraction of An and Bn, then we're going to be actually generic or we're going to be tending to some convex combination of mu and mu. Okay. So the actual definition of Cn we're going to use then is the following. We're just going to say that this is the floor of 1 over the minimum of beta n and n times An times Bn. Okay. Now, where does specification come into this? Well, here x from 0 to A1 is an allowed subword, right? It's in the language. And so in particular, that means that we can find something in G which is sufficiently close to x from 0 to A1. And then we can concatenate this as many times as we want, but by the way that G is defined in terms of allowing you to append things. So what do? We just pick Vn, which is going to be one such that the Hamming distance from Vn to Un is less than 1 over 2 Vn, is 2n, such that we have that V1 through Vn is in G for every n. Okay, And we're allowed to pick such a sequence by the right almost star weak specification property. Okay, well then what happens, we're defining these non-empty cylinder sets for every n, and because x is a closed subshift in particular, this implies that in the limit we actually get a point such that v1, v2, etc. is actually in x. So we get a point here. Okay, so what we're going to do is we're going to let f of beta, let's call this y here, we're just going to let this equal to y. Okay, and I claim that this is our reduction map. Okay, so y is continuous. Well, again, if you look at the nth digit of y here, this is only going to depend on finite many values of beta, and so it's continuous. Now, what if beta is in C3? Then it's tending to infinity, right? And so in particular, Cn is Cn divided by An times Bn is going to 0. And so we see that, again, except for set density 0, that y agrees with x. And so in particular, f of beta is in G of mu. Okay, now what if beta is not in Cn or C3? What happens? Well, then that means that infinitely often Cn is going to be some non-zero fraction of An times Bn. And so, if you just shift y enough, you'll start seeing larger and larger sequences that are distributed according to nu. Right? So in particular, because nu is not equal to mu, this implies that f of beta is not in G of mu. And so we have our reduction map. So just what I want to note, the reason we can't use the same specification property for just a general G delta shift invariant subset is because we did need being closed in order to actually say that if you take these finite words, you actually get something in the limit that's actually in your at a well-defined point. So we need a different form of the specification property that's stronger than the right almost star weak. Yeah, almost star weak specification property. Oh, I'm sorry, I did forget the weak here earlier. Thank you, I didn't notice that.
Yeah, we were wondering how you could prove this.
Sorry about that. Okay. Yeah, it's a lot of words. Okay. So this is our theorem for symbolic shifts. Now we actually do get a result for general dynamical systems, but with a slightly different definition of specification. Okay, so if xt is a continuous dynamical system, again with at least 2 invariant measures, and what's called the strong approximate product structure. The approximate product structure is another notion of specification that was first introduced by Feister and Sullivan, and we consider a strong version of it for our case. Then for an invariant measure mu, we have that g of mu is pi 0, 3 complete. So I'm not actually going to define the strong approximate product structure. It's even more lengthy than the definition of the right almost star weak specification property. But the idea is it is sort of similar, right? You want to take two generic points and just sort of interpolate between them in some reasonable way. Okay. So yeah, this is the second main theorem that we prove. So just examples of how our theorems can be applied. The dynamical system where x is equal to 0, 1, t of x is equal to 1 over x mod 1, and mu is equal to the Gauss measure. This is the continued fraction dynamical system. It's continuous and it has the strong approximate product structure, and so we get that the set of continued fraction normal numbers is pi 0, 3 complete. Similarly, if x is 0, 1 now, and t of x is equal to beta x mod 1, where beta is not an integer, but it's still greater than 1, and mu is equal to the Perry measure for beta. This defines the beta shift. In particular, if you look at the symbolic dynamical system you get by just taking the partition of the unit interval into intervals of size 0 to 1 over beta, 1 over beta to 2 over beta, so on, where this last little bit is going to be not of size 1 over beta, since beta is not an integer. What you get is you actually get a closed subshift of beta plus 1 to the z. Sorry, floor of beta plus 1 to the z. So in particular, because it's a closed subshift, it's pretty easy to show that it also has the right almost star weak specification property. And so we get that the set of beta normal sequences is pi 0, 3 complete. But then the map that takes a beta normal or a sequence and maps it to its just summing over the map t from floor of beta plus 1 to the n to 0, 1, given by xn maps to sum of xn over beta n. This is a continuous map, and so you can use this to show that the set of beta normal numbers is also pi 0, 3 complete, which follows from the set of beta normal sequences being pi 0, 3 complete. Okay, are there any questions?
How easy is to check those properties? I mean, because you have a nice theorem, but then it seems like, again, I'm not trying to be smart, but it seems like in some cases it's just easier to just do it, give an example, just do it, instead of checking that it satisfies this R, star, W thing. Or, no, maybe it's easy to check, but I'm not.
For some systems it is. Like for the beta expansion, it is pretty easy, because what you can do is you can always just insert a finite number of zeros at the beginning of any word, and then you get a valid expansion. The point is that a lot of dynamical systems you run into in real life are already known to have the specification property, like any subscript of finite type. Beta expansions, just so, and for subshifts in particular, it's like a combinatorial type argument, and I guess that's Yeah, I'm not really too sure how hard it is actually to check their specification or not, but I think.
Checking it in a system which you don't know the answer in advance, I mean, is it?
Um,
Because it seems that, again, it's the first time I hear about this, so I have no idea, but I'm saying it might be somehow tricky to check this.
It
Might-
might
I
be,
don't know.
but I think it's even trickier to like find
Do
a
it
system that
within
doesn't have
dynamic?
specification property. Like it's actually kind of hard to find counterexamples to things with specification.
Okay,
So
fair enough.
from that perspective, it is easy, but.
Okay, fair enough. Okay.
Thank you.
Thanks.